Yes, I can hear you.
Okay. Shahid, we were doing electron pair repulsion theory, right?
Yes, yep.
Did you see the video? And also I had shared a document with you for the angles.
Are you talking about this one, the shapes of molecules one, right?
Yes, yes, the molecule, right?
Yeah, I looked through it, yep.
Okay, because a part of it should be memorized, and part of it can be done in a way that you should view some videos which I have shared with you. This topic is very challenging in the paper, and also I think I have shared a worksheet with you also, because August has started. Now you should try to do some worksheet, mark the queries, let me inform on weekend, so we can do a class to discuss some queries, okay? We were doing, last time we were doing water molecule. I think we did water molecule. Now, what is the main theme of this topic? Electron pair repulsion theory says that electrons which are paired or which are lone, they force a molecule to adopt a shape in which the repulsion is minimum. Okay, I repeat, what is the concept? The lone pairs and the shared pairs of electrons in a molecule, they force the molecule to adopt a particular shape such that all the repulsive units are on maximum separation. Xenon tetrafluoride, you can see this diagram, it's a dot and cross diagram, and you can easily guess that xenon tetrafluoride is a molecule which you can now see on the screen. Look, this is xenon tetrafluoride, and you can identify that how many lone pairs are there. There are two lone pairs. Is it right that lone pairs are more repulsive than shared pairs? Shahid? Lone
Yes.
pairs are more repulsive than shared pairs. So whenever you talk about electron pair repulsion theory, you should remember to identify shared pairs and the lone pairs. Take another example, methane amine. I have shown the formula, and you can notice that there is a lone pair on nitrogen. Now I have broken down into formula which is called displayed formula. Now I circle it and I put a question mark here. Can you tell me that this lone pair will affect the shape?
No, because there's no other lone pair, right? It's only one lone pair.
Remember that lone pair is able to repel shared pair and also a lone pair. Lone pair is actually over repulsive. Lone pair will repel this bond and lone pair will repel this bond also. Lone pair is capable of repelling both the bonds.
Okay.
Now see this shape. Yeah. Now you can see the other angles are 109.5. They all are shared pairs. But can you see the lone pair, the contribution of lone pair? It has bent the molecules to 107 degree. This is a special case here. Do you remember this symbol wedge?
Yes, wedge.
This means out of the page, and this dotted line, it means in the page. What is the meaning of this wedge sign out of the page? And what is the meaning of dotted line in the page? So now you should remember that
5 hydrogen atoms combine with 1 carbon atom and 1 nitrogen atom to form a molecule of methanamine. The formation of exclusively single bonds fulfills the octet rule for both of the central atoms, carbon and nitrogen. Notice that there is one lone electron pair left on the nitrogen atom. There are 4 bonding electron pairs around the carbon atom. Therefore, the geometry of this atom is tetrahedral, with hydrogen, carbon, hydrogen, and hydrogen, carbon, nitrogen bond angles of about 109.5 degrees. There are 4 electron pairs around the nitrogen too, but one of them is the lone pair. A tetrahedral arrangement of the 4 pairs results in trigonal pyramidal geometry of bonds around the nitrogen atom. The hydrogen-nitrogen-hydrogen and hydrogen-nitrogen-carbon bond angles are close to 107 degrees due to the repelling effect of the lone pair. The VSEPR theory does not predict the overall shape of the molecule. In reality, this shape is variable, since CH3 and NH2 groups can rotate freely around the carbon-nitrogen bond. 5.
Chlorine trifluoride.
The molecule of chlorine trifluoride also has 5 electron pairs around the central atom. 3 of them form bonds, and 2 are lone pairs. Therefore, the molecule is T-shaped. Lone pairs are situated in the plane of the triangle. The interbond angles are approximately 90 degrees and 180 degrees. The molecule of
Bromine pentafluoride. All these examples are going to summarize our
molecules with 6 bonding electron pairs assume the octahedral shape. In a molecule of bromine pentafluoride, there are also 6 groups of electrons oriented towards the vertices of an octahedron. 5 of them form bonds, assuming the shape of a square pyramid. The interbond angles are approximately 90 degrees. Molecules
ethene molecule is an
The ethene molecule consists of 2 carbon atoms and 4 hydrogen atoms. Hydrogen atoms are capable of forming only single bonds. Therefore, the carbon atoms link together by a double bond to complete the octet for both carbon atoms. For the sake of clarity, it's more useful to represent bonding pairs as dashes. Since the valence shell electron pair repulsion theory treats a double bond in the same way as a single one, there are 3 groups of electron pairs around each carbon atom. Therefore, the geometry around each carbon atom is planar triangular. The predicted bond angles are 120 degrees. Since the repulsion between a double bond and a single bond is slightly stronger than that between 2 single bonds, the angles are a bit distorted. The overall geometry is planar, though that cannot be predicted from VSEPR theory.
This is the shape of ethene molecule. Organic molecules themselves have a long range of shapes, and whenever you look at the past paper, you can easily classify organic molecules and inorganic molecules. Normally, what students do, that inorganic molecules they memorize because they are famous, like water, ammonia, beryllium trichloride, A2Cl6, etc. But organic molecules, they give a big challenge because they are huge in number. So now give a heading. This will be our first thing to write today. Give heading ethene. You can make it a side heading. And after giving the heading ethene, you have to copy this screen. Give a side heading ethene.
Yep, ethene.
And copy this screen.
So there's no repulsion here because all of them are shared pairs, or like the repulsion is equal from everywhere, right?
This is the main idea. The molecular separation should be in such a way that electrons settle on repulsion. They move away. Now, let's revise this topic. We have done a good amount of it. Rule number 1, question mark, lone pair. How many lone pairs are there? Number 2, number of bonding pairs. Number 3, possible match. Number 4, possible shape. Number 5, rule number 5, possible angle. Now, this is a review that these are the rules to remember when you determine the shape. I already had told you that within the chapter of bonding, this topic, this shape wala topic is a very challenging topic. So now you have to copy this screen.
Okay. We're memorizing the angles. So if there's a compound with a lone pair, basically,
I show
we have
you
to memorize the angle for that.
I show you a review animation, and this topic is actually the idea. Now remember the idea that you have to count you should first try to make the dot and cross diagram, which is the fundamental thing. Once you make the dot and cross diagram, you will identify the bonding pairs and the lone pairs. If there are no lone pairs, then the structure will be simple. But if there are lone pairs, then actually you have to bend the structure. Lone pairs are more repulsive than shared pair. And as I told you that I'm sharing some videos also.
In determining the geometry of molecules, the valence shell electron pair repulsion model, or VSEPR, assumes that repulsions between electron pairs causes them to remain as far apart as possible. The geometry that the molecule ultimately adopts minimizes the repulsion between electron pairs. Click on one of the buttons to compare the geometries of these molecules.
Now,
consider the Lewis structures of ozone, O3, and boron trifluoride, BF3. Counting the number of VSEPR pairs of electrons around the central atom of each molecule, we find 3 VSEPR pairs. As far as electron repulsions are concerned, the VSEPR model treats double and triple bonds like single bonds. A lone pair occupies space around the central atom and is also counted as an electron pair. The electron pair arrangement that minimizes repulsion for 3 pairs of electrons is trigonal planar. The angles between electron pairs are 120 degrees.
Did you get this point? Trigonal, Shahid, trigonal planar. There are
Yeah,
no
that's just
lone pair in this
360.
game.
Yeah, for this one, it's like 3 shared pairs, and you just do 360 divided by 3 to find the angles between each.
So it's a very, very nice animation, but it's very long. I will try to share it with you. And
the molecular geometry is the arrangement of the central atom and the atoms bonded directly to it. In BF3, all 3 electron pairs around boron are bonding pairs. The molecular geometry is trigonal planar with bond angles of 120 degrees. In molecules with no lone pairs around the central atom, like BF3, the electron pair arrangement and molecular geometry will be the same. In ozone, there are 2 bonding pairs of electrons and 1 lone pair. The molecular geometry, that is, the arrangement of the 3 oxygen atoms, is bent or V-shaped. The lone pair versus bonding pair repulsion is greater than the bonding pair versus bonding pair repulsion. The 2 oxygen-oxygen bonds are pushed together slightly due to repulsion with the lone pair, and the bond angle is slightly less than 120 degrees.
Now, did you get it, Shahid, this idea?
Yes.
So
actually,
if we make a view to summarize this, actually what's happened whenever you are solving a question on this topic, which is shapes of molecule, you have to remember this idea that actually you have to see the number of shared pairs and number of lone pairs. Now I'm starting calculating the shape of the ions. Ions actually work in the same way. You have to calculate the number of lone pairs, number of shared pairs, and then you have to arrange them in such a way that electron pair repulsion is there. Now, there are different examples. For example, I draw outermost shell of the central atom, NH4 plus and NH2 plus. These are the 2 ions. You can see in NH4 plus, you can see in this one, NH4 plus, there are 4 electrons in the outermost shell, while in NH2 plus, there are, you can count 6 electrons. So when you make a bond and when you make an ion, the difference is there. So you always count bond pairs, lone pairs, and then you make a suggestion for the shape. For AS level chemistry, I tell you a very good idea that you have to remember the surrounding units. If there are 4 surroundings, tetrahedral is possible because lone pair is not there, right? I had shared you a table in the start, I think before the last class. So you can remember it. Now there are, look at this 1 and 2, but there are 2 lone pairs. Lone pairs always give a problem and the shape becomes angular. So this is the idea, NH3, NH4, NH5. I will try to share this also, but you can't learn it or you can't rectify it. Now, the different ions, when they are formed, they follow the same rule. The rule says count the number of shared pairs, count the number of lone pairs, and then decide the possible shape. Now, if the molecule contains a double bond, this is carbon dioxide. Look at this shape. There is no lone pair. I think you can identify from this. There is no lone pair. There is no lone pair. So the molecule is linear 180 degree. Now, this is a good point to remember. If there are no lone pair, then shape is easily predictable. If there are 2 surrounding, it's a linear. If there are 3 surrounding, it's a trigonal planar. If there are 4 surrounding, it is tetrahedral. So now give a heading, molecules with double bonds.
Okay.
And then give a heading, carbon dioxide. And copy only the circles I am making.
If there's 2 double bond pairs, it's called linear, basically, right?
There are 2 shared pairs in both sides, but there is no lone pair. There is no lone pair. Look, this one.
Yeah.
Other examples, now you can see SO4 minus 2 BRF3. Again, the main problem is the presence of lone pair. I want you to pay attention at this. Can you see how many lone pairs are there?
Or which one? BRF3?
Yes.
3. Sorry, 2. Nicely,
Look
I
at
think.
these two. Are they occupying extra space?
Yes, I think so.
So lone pairs are more repulsive. Now, let's have a review of some shapes. We have done water molecule, we have done ammonia molecule, we have done some other molecules. Remember, water molecule is important to call back because water is one of their favorite molecule.
The water molecule is non-linear, with a bond angle HOH of 104.5 degrees. The bent shape of the water molecule can be explained in terms of sp3 hybridization of the oxygen atom. 2 of the 4 hybrid orbitals present contain single electrons and form covalent bonds with hydrogen atoms. The other 2 orbitals contain lone electron pairs. The spatial arrangement of sp3 orbitals is normally tetrahedral, with an interbond angle of 109.5 degrees. However, the repulsion between a non-bonding and a bonding electron pair is stronger than the repulsion between 2 bonding pairs. So the bonding pairs are pushed together by the non-bonding pairs, and the resulting angle is 104.5 degrees.
So I hope you understood one thing, that the main problem is the lone pair. Practice in shapes of the molecule. Now, this is a table, and I will share this inshallah with you, so you can try to make these shapes. Again, I want you to pay attention look at this important concept. When there are 3 bond pairs, the shape is trigonal planar because there are no lone pairs. When there are 4 bond pairs, no lone pair, shape is tetrahedral. When there are no lone pair, shape is a memory. But as soon as lone pair appears, then shape becomes a problem. So normally students isolate questions, they divide questions in 2 types. There is a lone pair or there is no lone pair. If there are no lone pair, the game is simple. There are 3 shared pair, trigonal. 4 shared pair, tetrahedral. 4 shared pair, tetrahedral. 6 shared pair, octahedral. 6 shared pair, octahedral. But as if the structure contains lone pair, then obviously the structure will change. Now you have to give a new heading. Shapes of molecule is over. And you have to give a new heading, electronegativity.
Okay.
Electronegativity concept is now first to be discussed. Now, when you make a covalent bond, when a covalent bond is formed, there is a shared pair of electrons. This electron pair is being shared by both the nucleus. This is the main core idea of a covalent bond. Now, what happened? That ability of an atom to attract the electron pair in a covalent bond to itself. This ability is called electronegativity. So what is the concept? When a covalent bond is formed, there is a shared pair of electrons which is being attracted by both the nuclei. Now, every nucleus has the ability to attract the shared pair. This ability is called electronegativity. So now you give the heading electronegativity and write under it the ability of an atom to attract the electron pair in a covalent bond to itself. This definition is there and its value is relative. Relative means it's not an absolute number. It is a relative number. It's a comparison number. Sorry, you have to copy this.
Yeah, done.
Then copy this screen.
Done. Yeah, copied it down.
Electronegativity is a relative number. Its value increases across the period. Its value decreases down the group. And fluorine has the highest value. Now, I hope you remember this concept when we were doing topic number 2. I told you that these type of statements are very common in chemistry, and they are called, what we call them? They are called, what we call them?
Trends.
Trends. For every trend, you should remember that there is a sketch. There is a sketch. There is a reason to remember, and there is some type of exception. Remember, in A-level chemistry, whenever you get a trend, you should know how to draw its sketch, what is the reason for the trend, and if there is an exception, you have to explain the exception. The word exception or contradiction. So can you repeat for me? For every trend, there are 3 features to remember. What are the 3 features to remember? How to draw the sketch. What is the reason for the trend? And if there is an exception, you have to determine and explain the exception. Okay, can you repeat for me? What are the 3 features of every trend in chemistry?
How to draw the sketch, the reason,
Yes.
and then if there's any exception to the trend.
And also the reason for it. Okay. Now,
yes, I said the reason, sketch, and
okay,
then the
sorry.
reason for the trend.
Okay, fine. Now copy this box. I'm crossing what is not supposed to copy. The topic we have started is electronegativity, and these are 3 important features of this topic. You can see these are the trends.
Okay, writing. Done.
You have to copy this. This is easy way to remember. Electronegativity trend. Now look at this. Electronegativity is the power of an atom to attract electron density in a covalent bond. Now this is a scale. The higher the value, the more electronegative the element. Fluorine is the most electronegative. It has electronegativity in a scale value of 4.0. Now look at this diagram. Fluorine 4.0, lithium 1.0, beryllium, boron, carbon, nitrogen, oxygen. So in a period, left to right in a group, up to down, you can identify them, and the table we have no. You can identify very interesting thing if you notice here, which is called the noble gases. Can you notice that there are no values for noble gases?
Because their outer shell electron is already complete, so they don't
Because
really interact.
noble gases, are they willing to make a covalent bond or any type of bond? Do you think they will be interested of making a bond?
No, because
Or
their
they
outer
are
shells
stable?
are full.
They are full. So
Yeah.
remember that the concept of electronegativity is associated with what? Very important concept to understand, that the concept of electronegativity is associated with covalent bond. It is not a standalone concept. It is a subtopic of covalent bond. Okay. Now, you have to make a quick line with me that whenever you come across a trend, what you should prepare in the notes, whenever you are coming across trends in chemistry, for every trend, you have to be able to draw a sketch. This is the fundamental thing. You should know the reason, and you should be able to locate and explain any exception. You have to copy this screen.
Yeah, done.
Now, we have explained this concept. Now we move forward to our next title. Ionic character in a covalent bond. You have to give this new heading.
Yep, done.
Now, this is a very important concept in O level. People made a concept that there is a covalent bond, which is normally between two non-metals. There is an ionic bond between a metal and a non-metal. There is a metallic bond between the atoms of a metal. This was our O-level concept. So in O-level, the bonds are considered to be separate entities. For example, in O-level, if you can remind that a bond between sodium and chlorine is expected to be ionic. Bond between chlorine and chlorine will be expected to be covalent. Bond between sodium and sodium is expected to be metallic. This is our O-level memory. In A-level, we make a new concept. We see that ionic, covalent, metallic, actually these are relative bonds. Any covalent bond can have some ionic character. Every ionic bond has some covalent character. It means that ionic and covalent characters are overlapping to each other. There are many covalent bonds which have ionic character, and there are many ionic bonds which have covalent character. So this will be the first important concept to understand. Now make this concept, after giving the heading, write under it that every ionic bond has some covalent character. Every ionic bond has some covalent character while every covalent bond
Could you repeat that again?
Every ionic bond has some covalent character, and every covalent bond has some ionic character.
Okay.
Now, we start this concept when a covalent bond is established between two atoms which have a considerable difference in electronegativity. A charge distribution appears. This is called ionic character. Now consider a bond between hydrogen and chlorine, HCl. Now there is a shared pair of electrons. Now you can guess one thing. What is the atomic number of chlorine? What is the atomic number of chlorine? Atomic number of chlorine is 17. What is the atomic number of hydrogen? It is 1. It means this nucleus has a charge +1. This nucleus has a charge +17. This is a lone pair with a charge -2. Now, can you guess, chlorine or hydrogen, who will attract the shared pair more effectively? Chlorine has a +17 charge. Hydrogen has a +1 charge. The electron pair has -2. So can you guess who will attract the electron pair more effectively?
Is it the larger molecule, right?
No, just use physics. +17, look, +17 is attracting -2 and +1 is attracting -2. Who will attract the central electron pair more strongly? I'm asking a very simple question. It's a physics simple question. +17 is attracting -2 and +1 is attracting -2.
So the larger one, +17.
Larger is not a question. The name, the element. There are two elements. Who will attract chlorine? That's a very simple question. I don't know why you're taking so time. Chlorine will be attracting the shared pair more effectively. Now what will happen? The electron density will be more towards chlorine. So you will show this on chlorine and this on hydrogen. This is called the difference of electronegativity, and this is called the ionic character. And if this happens, such a bond is called polar bond. If polarity appears, plus minus appear in a covalent bond, it is called a polar bond. So this is a case of polar bond, and polarity is a character which appears when there is a difference of electronegativity. This is electron density map. You can see that more electron density is around bromine. Look at this, fluorine is more electronegative than hydrogen. Fluorine is actually the most electronegative in the whole table. So fluorine will pull out the electron density around. This is called electron density map. Can you see where the density, where the shaded area is more?
Yes.
Around what atom? There is more density, more shaded area.
Oxygen.
Oxygen. Why? Because oxygen is more electronegative, and in our chemistry we call this electron density map. We call it electron density map.
Okay.
Silicon, phosphorus 3, and sulfur 2 chlorides are covalent compounds. The polarity of the bonds decreases from silicon to sulfur. Silicon,
The bond in a diatomic chlorine molecule is of course purely covalent, since the electronegativity of the linked atoms is identical. The bond in a diatomic chlorine molecule is of course purely covalent, since the electronegativity of the linked atoms is identical. If the difference between the electronegativities of the bonded atoms is very small, the bond is relatively non-polar. But if the difference is large, the bond is polar. The larger the difference, the more polar the bond. If the difference between When two identical atoms link together by a covalent bond to form a diatomic molecule, such as the hydrogen or the fluorine molecule, the electron density is distributed evenly between the atoms. However, when two different atoms combine, for example, hydrogen and fluorine, the electron density distribution is no longer symmetrical. Fluorine attracts electrons more strongly than hydrogen, and the electron density is shifted towards fluorine. Since there is a greater share of the electrons around fluorine, this end of the molecule becomes negatively charged. The opposite end of the molecule has a corresponding positive charge. The charges are described as delta minus and delta plus, respectively, to indicate that the charges are small, smaller than the unit charge of an electron. The hydrogen fluoride molecule is described as polar, which indicates that there are two oppositely charged poles in it. The ability of an atom to attract electrons in a chemical bond is known as its electronegativity. When
A non-polar covalent bond forms when the combining atoms have the same or very similar electronegativities. That is why the covalent bond between atoms of the same element is always non-polar. Two different elements can form a non-polar bond only in certain specific cases. For example, the sulfur-carbon bond is practically non-polar because the two elements are characterized by very similar electronegativities. A non-polar covalent Other covalent bonds are polar to some extent. The degree of polarity increases with the electronegativity difference between the bonded atoms. For example, there's about a 1-unit difference between the electronegativities of sulfur and oxygen. Consequently, the sulfur-oxygen bond is strongly polar, with a partial negative charge on the oxygen atom. Other covalent The electronegativity of sodium is 1.6 units lower than that of sulfur. The polarization of the sulfur-sodium bond is so strong that we can expect the bonding electron pair to move to the sulfur atom completely. In this case, a pair of ions is formed, and the bond takes on ionic character. Ionic bonds are polar by nature, but can also show some covalent character. When the cation is small and carries a large positive charge, it tends to attract electrons towards itself. On the other hand, electron clouds in large anions with a high negative charge are easily distorted. If two such ions form an ionic bond, some of the electron density of the anion is shifted towards the cation. This in turn gives the ionic bond some covalent characteristics. For example, we can expect some covalent character for the ionic bond in lithium iodide. The electronegativity
I made a long discussion and animations were there. So let's come back to the main point again. When a covalent bond is established, if there is a difference, large difference in electronegativity, the molecule will become polar. And if this polarity appears within a bond, it is called the difference of electronegativity, and this is called polarity of a bond. Now you have to copy this screen.
Yeah, done. Got it done.
Now, you have to quickly recall for me that this is the concept of density model. This is the concept of electron density difference, and this leads to polarity. You have to copy this screen.
Yeah, done.
Now, this is called electron density map. Electron density shift towards chlorine. Electron density shifts towards chlorine. So now copy this.
It shifts more towards chlorine because like it has a higher electronegativity,
Yes, now you got the concept, and chlorine is more electronegative than hydrogen. This is a very important thing to remember, that electronegativity is the source of this polarity. Now, this is called the ionic character. Have you copied it?
right? Yes.
Okay, now copy this.
What's the S thing again?
Sorry.
The plus. What's the plus minus S thing?
No, this symbol I have mentioned here. Look in this. Look at this screen. This symbol means partial charge.
Partial charge. Okay. Yeah, you can go to the next one.
Now copy this.
Yeah, done.
So in any bond, if the electronegativity difference is not zero, there will be some ionic character. Now give the heading dipole effect.
Dipole. Okay.
Dipole, the word dipole means a dual polarity. This is called a polar molecule. It is just like in physics, when a sphere has negative and positive charges, this is called dipole effect. So in hydrogen and chlorine, this is a polarity, and every covalent bond has a dipole. Dipole means one positive terminal and one negative terminal. You have to copy this.
Okay. Yeah, copied.
Now, example one, the polarity, because I think you take physics also, so you can understand this concept. Polarity is like a force. If the forces are in a straight line, the resultant force would be zero. Can you tell me in the second diagram, this one, why the force is not, why the resultant force is not zero?
Because wait, is it? Are you talking about the second one?
Because, why?
Are you talking about the first or the second one?
No, I've made an arrow now. Why the resultant
Oh,
force
okay,
is
this
not
one.
zero?
I think it's because due to the vertical
Yes,
side of
because
the
they are
vertical.
not on the same axis.
Yeah.
Because they are not on the same axis. So dipole effect is like a vector effect. Now see this example, CO2. There are two dipoles and the resultant dipole is zero. Why the resultant dipole is zero? Because of this idea, the two forces are acting in the same and opposite direction. So carbon dioxide is overall a non-polar molecule. Look at this, dipole is not zero. Now you have to write under it dipole interaction, dipole interaction is analyzed like a vector. You have to copy this screen now.
basically the dipole would be the resultant force, is it basically?
It is like a resultant force. Now give the heading polar molecules. So give this heading and we will inshallah do this topic in our next class. Okay.
Okay.
So you are required to do the homework and we will inshallah continue in the next class. Allah Hafiz.
Okay. Okay, Allah Hafiz.